like we never left. There's a lot of ways that we could solve this problem, right? But if we have the 2 first, that was the troublemaker. Then we had to have a 2 there, and we had to have a 5 here is what we determined. And then, so that means I only have one option. And for my third option, I can have 1, 3, or 4, right? The remaining elements, which means I have 3 options. 1 times 1 times 3 is 3 options. If I have a 3 first, 1, 2, 3, then I am forcing 1 to be first, or forcing 3 to be first, meaning I only have 1 option, right? But then we said, okay, I have 4 options and 3 options because of no repetition. 4 and 5 first look the same, right? I'm forcing the 4 to be first, meaning I only have 1 option. But then, as long as I don't have any repetition, I have 4 options and 3 options. And same thing here, 1, 4, 3, which is 12. What could you have done? You could have lumped all these special cases into one, right? And you could have said, or that might look like this. I have 3 options, right? Could be 3, 4, or 5. And then I have 4 options. Because then all of a sudden the forbidden 1 and 2 are back on the table, but I've already used 1, and so now I have 4 to choose from, and followed by 3, which is going to be the same 36, 12 plus 12 plus 12, or 36. Doesn't matter which way you slice them and dice them. And so together, remember, this is only for 3, 4, or 5 first. There are 36 options. Okay. So what we can do is we can say 2 first plus, or maybe I'll start saying or, which is plus 3, 4, or 5 first, which is 3 plus 36, which means that there are a total of 39 permutations greater than 250. There are 4 questions for you to work on, but just because I slipped behind a little bit because I got too blabby, we'll leave those because I want to introduce the next set of questions instead if we're going to spend time on any. But the solutions will be in the notes so that you can look back and go through them. The key thing to think about is whether you're allowing repetition or not, right? If you're not allowing any repetition, then it's a permutation. And then you can use that permutation formula. But let's see here. I think you can always use the slots. Just gonna scan my. Okay, the first one might be a little tricky with the slots. No, you still can. So what did we do to simplify our counting earlier when we said, okay, I've got a couple of different scenarios here. Where is it? The greater than 250s, right? I had kind of conditional options depending on what the first digit was, right? And so the easiest way to break that up was to say, okay, well, how about I just figure out how many there are with the 2 first, and then how many there are with the 3 first, and then what we found was we could lump these all together, 3, 4, 5 first. But what we did was we partitioned all these options. So that's what we're going to talk about next. Partitioning a set. So a partition of a set is a set of one or more non-empty sets of A. So A1, A2, A3, all the way up to something, probably N, such that every element of A is in exactly one set. Okay? And so I use partitioning all the time when I'm counting, right? And so usually if I'm counting how many are in the room, I count by 2s, right? And so you're either in my set of 2 or you're not, but eventually you will be in a set of 2, right? And then that just speeds up my counting, right? And so that's exactly what we're doing. All we're doing is counting really in this section, okay? But what we have symbolically is that, okay, if I have the union of all of these partitions or subsets of A, and I take the union of all of those, it has to be A, meaning every element has to be in some partition of A. Okay. If I is not equal to J, so meaning that as long as I have different subscripts here is all that's saying. So if I is not equal to J, then the intersection, that's from last week, right? The intersection of AI and AJ has to be the empty set, right? Because they can't have a shared element, right? Meaning that, okay, every element has to be in some partition of A, right? But you can only be in one partition, right? This notation, this generalized notation is going to come up quite often. So it's good to kind of get the hang of it, right? And so if I is not equal to J, so if these two things are different, right, then AI and AJ, well, these two different sets, right, have to be the empty set. So as an example, there are lots of ways that we can slice and dice a set. So if we have a set A, B, C, D, then some examples of partitions are I can let A be on its own, B be on its own, and then C, D smushed together in one set. That's a partition, right? And so we're really just slicing this set into different combinations. We can talk about A, B together, C, D together, right, in 2s. That's how I count. Or if you're counting 1, 2, 3, 4, 5, 6, 7, that's the same as A, B, C, D, each in their individual partition, right? So the basic law of addition says that if A is a finite set, right? So we're not talking infinite sets, we're talking finite sets. And if A1, A2, all the way up to AN is a partition of A, then the cardinality of A is going to be the cardinality of A1, the cardinality of A2, all the way up to the cardinality of AN added together, right? That's pretty straightforward, I think. If each element can only be in one of these partitions, and I look at the cardinality of each partition, then of course they should add up to the total cardinality. But I also want to use this to remind you of the summation notation from last week, right? The sum of the cardinality of A subscript K, where K goes from 1 to N, right, is how you would summarize this summation, right? Good. We can rephrase it in terms of the union, right? So the union of A1, A2, all the way up to AN has to be A, right? And as long as there's no overlap in these partitions, right, then the cardinality of all these guys together, well, we can say that that's the same thing as the cardinality all added up together. It's the same as before. So the key is going to be to find partitions where there's no overlap, right, but that still cover all the possible elements of the original set, right? And so if we think of everyone in the room as the possible elements, right, I could count by fives. I could count how many are in each row, right? Each row could be a partition because a student can only be in one row at a time, right? And then I can add up those rows, right? And so there's lots of ways that we could break it up, but you just want to make sure that there's no overlap. So we could add the number of students who are freshmen, sophomores, juniors, and seniors, which doesn't really mean anything to me, but I know there's no overlap, right? And I guess there are people who are in none of those, but there's no victory lap in high school. Are these for university too? Maybe, I don't know. Doesn't matter. You just want to be careful, like I said, that there's no overlap, right? So if you're talking about majors, then if you're counting how many are in each major, then there's a potential for double counting because there's such a thing as a double major, right? And so you don't want to do that. But as long as your partitions are distinct from each other and take up the entire set, then you're safe. For an example, the sophomore computer science majors were told they must take one and only one of the following courses that are open only to them: cryptography, data structures, and JavaScript. The numbers in each course, respectively, for sophomore computer science majors were 75, 60, and 55. And so how many sophomore computer science majors are there? This one, it was open only to them, but then they must take one of these and only one of these courses, right? And so these courses are a great partition for these sophomore computer science majors, which means that we can talk about it as cryptography is a partition, data structures is a partition, and JavaScript is a partition, right? Because it satisfies that there's no overlap, but also includes every element in the set, right? But really, the only thing I'm looking for here is 70 plus 60 plus 55. Which is 190. This one needs a bit more space, so I'm going to go ahead and just add a page right away. And We've seen this question or this type of question before, right? In set theory, we talked about sets and Venn diagrams, right? And so it was determined that all junior computer science majors take at least one of the following courses. So now we're talking about at least one of these, right? And so now we're not just restricted to exactly one: algorithms, logic design, and compiler construction. Assume the number in each course was 75, 60, and 55, respectively, for the 3 courses listed. But then further investigation indicated 10 juniors took all 3 courses. Right? 25 took algorithms and logic design, and 12 took algorithms and compiler construction, and 15 took logic design and compiler construction. Now we want to know how many junior computer science majors are there. You could answer this with just your knowledge from last week, right? But really, what are you doing? You're making partitions, right? So we can visualize these partitions. First thing I'm going to do is I'm going to let A denote algorithms, the algorithms course. L denote the logic design, and C denote the compiler construction. Just for some shorthand. It's good to get in the habit of just denoting these shorthands and just giving a legend. If you forget, as long as you use obvious letters, it's okay. But I'd love to see it. Because what are we going to do? Let's make a nice big Venn diagram here. If I have 3 things, I need a 3-circled Venn diagram, which I showed you last day is going to look something like this. The rectangle is the universal set, right? Which we always use even if there's nothing in it, right? Even if everyone's in the circle. But then I'm going to have A, L, and C here. So what I mean by making partitions is I'm going to let each area here be its own partition. The total area of A has to total 75. Right? But there's overlap there. And so what I want you to do is you always start in the very, very middle, and then you can work your way out. Okay? So let's see here. I want you to 10 juniors took all 3 courses. So 10 is going to go in here. Now those 10 have already been counted. So even in the overlap, you're going to have to remove those 10 before you can move on. 25 took algorithms and logic design. So algorithms and logic design, and now I forgot the number already, 25. So this whole area has to be 25, but I already have 10 in there, right? And so I'm going to show 25 minus 10 makes 15. I'm gonna run out of colors pretty quick here. 12 took algorithms and compiler construction. Algorithms and compiler construction, but 10 of those have already been written down. And so I have 2 here, right? 12 minus 10 makes 2. And I guess I should, 12 minus 10 is 2. And then 15 took logic design and compiler construction. And how about blue? 15 minus 10 leaves me with 5. Yeah. Now I'm gonna write down so I don't have to scroll around and look so much. Let's do this. The cardinality of A is 75. The cardinality of L is 60. And the cardinality of C is 55. Just grabbing those numbers from up here. So to find, so this total circle of A has to total 75. But in order to make the partition, right, of this only A space, I have 75 minus 15 minus 10 minus 2, which is something 50, 48. I'll confirm. I don't trust any math, but it's good. Logic design is a total of 60, but I have to subtract 15, then 10, then 5. 30. And finally, uh-oh. Doesn't want to do it. 55 minus 2 minus 10 minus 5. It's 38. And I think we said that there were none that took none. They take at least one of the following courses. So now, how many junior computer science majors are there? With the partition, we can add up all these spaces and we can find how many there are. And so the total computer science majors, or the cardinality of it, is 48 plus 15 plus 30 plus 10 plus 2 plus 5 plus 38, or some version of that. I don't think I have it pre-cooked here. So here we go. 48 plus 15 plus 30 plus 10 plus 2 plus 38. I get 148 total, which would be very different, right, than just adding up, right? If you just went for it and did 75 plus 60 plus 55, you're going to be quite a bit off because you need to subtract the overlap. Another way you could do it is do that total and then subtract the overlaps. That's fine. And then add it back in if you've taken it out too many times. But I find visualizing it is nice and easy. But if you were to add up all the sets, right, for 2 sets, so just if we had 2 courses, right, what you could do is you could take the elements in set 1, the elements in set 2, and then subtract the overlap, right? That would look like this. and then subtract the overlap. We saw that last day. So here, subtract the overlap. For this 3 set, so we just looked at 3 sets, and so there is a law that we could use, but like I said, I find the Venn diagram more, I don't know, more helpful, but you'd be doing the same thing if you wanted to find the cardinality of A1 or A2 or A3 by adding up the cardinality in A1, A2, A3, regardless of overlap. And then you subtract the overlap, but now you're subtracting all 3 overlaps, right? Which means that, okay, that's good, but then you have to add back in that overlap in the middle. Okay, so here you subtract the double overlap, overlaps maybe, and then add the triple overlap back in. Right? Because if you imagine these as kind of, layers, if you add up A plus L plus C, now you got 3 layers, right? So then you subtract the overlaps, all 3 of them, but then you're left with no overlap here in the middle, so you have to add it back in, right? We do that intuitively. We don't need this set law to tell us to do that if we just draw the Venn diagram. So that's why I would say all our questions we're going to be able to solve with a Venn diagram. So I would encourage you to use that. We'll do the first one together, and then I'll give you a little bit of time to work on those exercises, and then we'll just kind of go through them briefly together. So I'm worried about timing. So a group of 30 students were surveyed, and it was found that 18 of them took calculus and 12 took physics. If all students took at least one course, how many took both calculus and physics? And we're going to use a Venn diagram here. So I'm going to let calculus be C and physics be P. I'm going to start by drawing them like this with an overlap, but what we're going to find, right, is that there can't be overlap, because if I have 18 here and 12 here, can there be overlap? No, right? 18 plus 12 gets me to 30. So since 18 plus 12 equals 30, no students took both. What if we changed it? What if we found out that 5 students did not take either of these? What does that look like? We're going to keep 18 in calculus and 12 in physics. But now, because the total has to be 30, right? Then there must be an overlap of 5, making 13 here, and 7 there, right? I'll just confirm 5 plus 13 plus 5 plus 7 does equal 30. So we're good. Still, C and P, calculus and physics, still a total of 18 in the C circle and still a total of 12 in the P circle, but now there has to be some overlap because we had to make room for these 5.
Either one of them.
These guys, these 5 are not taking it because they're outside the circles. But if the total has to be 30 still, then that's what smushes these two together, the calculus and physics. And that's maybe not clear because it's in part A, but total must still be 30 is the key. So I want to give you 10 minutes to work through these exercises, but I want you to focus on 4 and 5. Okay? You can have a look through 2 and 3, but 4 and 5 are closer to what I would ask you on a test. And so let's see here, 434, 44. I'll pause this video. And if you need paper, I'll bring it out again. Here, there. Pick up the recording again. Okay. And I'm still sharing my screen. That's a good thing. All right. List all the partitions of the set A is kind of tedious. That's not something I would get you to do on a test. And so that's why I'm kind of, you can try it and the solutions are here. And then I just want you to think about, show that 2n where n is in the set of integers and 2n plus 1 where n is in the set of integers is a partition of the set of integers, right? Does it have 2 unique separations? And then I want you to describe this partition using only words. That's more for kind of playing around with a little bit of proofs, right? And also just looking at some of this notation, right? This is a one-time question, and so I can't do it on a test unless you tell me you absolutely want it on the test, then fine. But we're going to look at this one and 5. But here are the solutions. So list all the partitions on the set. You can have it in singles, you could have it in 2 and 1, or you can have it in groups of 3. And so those would be the different ways of slicing and dicing this set. And for the proof, that 2n, right, which is the set of even numbers, including 0, right, and 2n plus 1, where n is in the set of integers. So what I've done is I've just used some values of n, some reasonable values of n to see a pattern. And then I see that it looks like 2n plus 1 is the set of odd numbers, right? Excluding 0, because there can't be any overlap. Right? 0 was kind of the pickle there, right? But because 0 doesn't show up in the second set, there's no overlap, right? And so I see I have all odd numbers, or all odd integers and all even integers, making a perfect partition on the set. here's what I wanted you to work on. We have a survey of 90 people, 47 of them played tennis and 42 of them swam. So if 17 of them participated in both, how many of them participated in neither? So same idea, you're gonna start in the center with the 17 that did both. Notice that I used T to denote tennis and S to denote swimming. And I found that this area of 30 are the ones who only play tennis, right? And 25 only did swimming. But I have a survey of 90 people, so I can find that 90 minus 30 minus 17 minus 25, which is 18, did neither. Good. Blackberries and iPhones and Androids. Now, we're not going to work through this together because I know you worked on it, but I do want to just talk about the different counts, right? Because I didn't do the math on here, but you're going to start here in the center with the 3 that had all 3, right? I guess I would have an iPhone and a BlackBerry. I've got a BlackBerry somewhere hidden in a drawer somewhere, just in case I'll need it, right? I'll never need it. But then 37 had an iPhone and a BlackBerry, but not all 3. 9 had an iPhone and an Android, but not all 3. 5 had a BlackBerry and an Android, but not all 3. And then 11, 30, and 13, making for a total of 192 outside. Where did I get that 192? Because I have a survey of 300 people. So that has to be 300 minus 11 minus 37 minus 30 minus 9 minus 3 minus 5 minus 13, putting me at 192. Part B, how many people owned a BlackBerry but not an iPhone? So they owned a BlackBerry but not an iPhone, so that's 30 plus 5. And how many owned a BlackBerry but not an Android? BlackBerry but not an Android is 37 plus 30, which is 67. Good. Any questions about that one? So I'll definitely get you to do a 3-set Venn diagram on the test, but I'm expecting it to be just 100% across the board. So we've talked about the rule of products where the order is important, right? And so such as the batting order of a baseball team. In other cases, it's not important, right? So if you think about the order that you place coins in a vending machine, right, then the order doesn't matter, right? The total, you get to the same total, hopefully. Or in listing the elements of a set, if we bring it back to sets, then the order doesn't matter, right, as the elements of a set. So I've highlighted here, order is important in permutations and order is not important in combinations. Okay? And so what we're going to talk about now is combinations. The tricky part for us is going to be reading a question and figuring out, okay, is order important or is order not important, right? Because that'll determine which formula to use. So as an example, how many different ways are there to permute 3 letters from the set A, B, C, D? So we have 4 elements and I want to grab 3 of those and make permutations. So we know from the permutation counting formula that there are P43 or 4P3 ways of doing that. And we also saw in the previous section, I guess, that we could write that as 4 factorial over 4 minus 3 factorial, right? Because recall, Pnk is n factorial over n minus k factorial. So P43 is 4 factorial over 4 minus 3 factorial, which you can expand to make 24. How many ways can we select a set of 3 letters from A, B, C, D? So we're not concerned about the order of the 3 letters. And so what can we do? We have A, B, C, A, B, D, A, C, D, and B, C, D are the only combinations that are possible. And so we're looking for 3 element subsets of the set A. The notation that we're going to use for choosing 3 elements from 4 is this 4 choose 3 is how we're going to read this. So we've got these brackets. In fact, one of the questions or exercises that I assigned last week included the choose function, which is what we're going to call this. But you could just treat it as one animal for that section. But now we're going to see what it does. So 4 choose 3, or sometimes we can use the same notation as P and K. But you're going to read it as 4 choose 3, which is the number of combinations for 4 objects taken 3 at a time. So order doesn't matter, you're just taking 3 of these things. This is called the binomial coefficient. And so let n and k be non-negative integers, then this binomial coefficient n choose k, which I'll write here, n choose k represents the number of combinations of n objects taken k at a time, and is read n choose k. And I'm going to hold off because I've got an example here where I'll bring it up. But yeah. So the formula, we're not going to prove this one, but if n and k are non-negative integers, with k being anywhere between 0 and n, right? I can only choose between 0 and n things from n things. Then the number k element subsets of the n element set, so the number of ways I can choose k things, is going to be this n choose k, which is going to be n factorial divided by n minus k factorial. That looks familiar, right? But then we're going to multiply it by k factorial. Okay. One thing to notice, if I give you 4 things, trying to grab 4 things, they don't have to be the same things, but 4 fingers, right? And how many ways can you choose none of those? There's only one way that I could choose none of these fingers, right? I don't choose you, I don't choose you, I don't choose you, I don't choose you. That's the only way that I can choose 0 out of these. On the flip side, how many ways are there that I could choose all 4 of these? I choose you, I choose you, I choose you, I choose you. Right? That's the only way that I can choose all 4. Right? And so as a fact, n choose 0 is 1. It's only one way to choose 0 things. And n choose n is 1. There's only one way to choose all n things out of n things. let's think about a coin. Right? So we've got an evenly balanced coin and it's tossed 5 times. How many ways can 3 heads be obtained? You don't have to have this, but I do want to show you what we're talking about. So I'm tossing a coin 5 times. We can use that same tree diagram that we were using earlier, right? Where we can say, okay, I start here and I'm going to give myself lots and lots of space here. I flip a coin, it's either heads or tails, right? If it's heads, then I flip it again and I can get heads or tails, right? Notice that this is going to be flip number 1, number 2. And so I'm going to have 5 layers. I guess I shouldn't have made it so lofty already. It's tricky because you need to have enough room. I'll try to use just one line for each, right? Heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, right? They're independent events. And so it doesn't matter what happened before. If I flip again, I can get heads or tails with the same probability. But we're not talking probability here, but I think we can all be convinced. Oops. See how this gets out of hand pretty quick. Tempted. No. 5 flips. Sloppy. Started out so nice, didn't it? Tail, head, tail, head, tail. I think you get the idea. So now, what can you do? If we want to talk about in how many ways can 3 heads be obtained? This is one way that we could visualize all the different options, and we can use this to map out all the ways that we can get exactly 3 heads. Okay. So here, if I do a heads first and then I do another head, then the only option is, well, I can stop here. I can go here, but then I have 3, so then it has to be tail, tail after that. Or, now when I'm saying or, you have to add these guys. Sorry, that's probability. That's not for us. But it's true. Head, head. What if I went to tail and then a head and then a tail? That's 3 heads. What's another way that we could do it? Head, head, tail, tail, head. Uh-oh. So what you're going to find is you can run through all these different options and accumulate all the different ways that you can get 3 heads. Or you can use the choose function, right? And so the choose function says, okay, if I have 5 flips, right? How many ways can I have 3 of those be what I'm picking, right? A head, for example. And so what we're going to find is that, see next page for tree diagram. I'll add that. But really what we're going for is 5 choose 3 is that there would be 5 choose 3. Oh, and I shouldn't jump straight to 10 here, but 5 choose 3 ways of arranging these, right? Head, tail, head. Sorry, I forgot there were 5, not 3. It's easier with 3. Easier to visualize too, but we're flipping 5 times. So if we're using the formula, right, n factorial over n minus k factorial times k factorial, I can write this out as 5 factorial over 5 minus 3 factorial times 3 factorial. To keep it in the space. The trick that I'm going to use is I'm going to expand 5 factorial until I hit the larger of these factorials, right? 5 minus 3 factorial is 2 factorial, 3 factorial, so I'm going to go to 3 factorial. So I get 5 times 4 times 3 factorial over 2 factorial times 3 factorial. The reason I did that was so I could cancel 3 factorial and 3 factorial, which I'm allowed to do because it's multiplying. Right? I've expanded the 5 factorial to be 5 times 4, and then I just lumped up 3 times 2 times 1 into 3 factorial so I could cancel them. Sneaky, right? But then I'm left with 5 times 4, which is 20, divided by 2 factorial, which is 2 times 1, which is 2. So 20 divided by 2, which makes 10. You can try it on your calculator, right? I've got an NCR button or NCR button on your calculator. You can try it. Yeah. Yeah.
What happens if it's minus?
We can't do factorial on a negative number, but you also can't choose a negative number of elements. So it's okay. It's not going to happen. Right? You have to have a positive number of things to pick from, and then you have to pick a positive number of things. But yeah, the factorial doesn't work for negative numbers, only positives. What if we had to determine the total number of ordered ways a fair coin can land if tossed 5 consecutive times? So just all the possibilities, right? And so, well, what are my options? If I toss a coin 5 times, then if we talk about heads again, right, because we talked about heads, right, talking about tails would be the same, right? But we only need to talk about one of those scenarios. I could have all 5 heads, or I could have 4 heads, or I can have 3 heads, or I can have 2 heads, or I can have 1 head, or the one that we love to forget is I could have 0 heads. That's an option. Toss it, and I could get all tails, and then I'm left with 0 heads. And so what we've done there is we've partitioned the set, right? We said, okay, all the possible ordered ways that a fair coin can land if I toss it 5 times, right? It can be any one of these. I could have 5 heads, 4 heads, 3 heads, 2 heads, 1 head. So we could get 5 heads, or 4 heads, or 3 heads, or 2 heads, or 1 head, or 0 heads. You don't want to forget about this little guy. Maybe it's just me. I always forget about the 0 option. I know it's not just me because I see a lot of students forget about it too. But it is a totally valid outcome, right? Tails, 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 tails. Yeah. So in 5 tosses, 5 heads, right? Then we could do that diagram, right? And we could count how many ways, but really the shorthand for that would be 5 choose 5. Right? Forcing me to choose 5 heads out of 5 tosses. Plus the number of ways that I could get 4 heads out of 5 tosses, which is 5 choose 4. Plus, remember, we're figuring out the total number of ways that we could toss this coin, right? 5 choose 3, plus 5 choose 2, plus 5 choose 1, plus 5 choose 0. Some of these we already know, right? Because we said n choose 0, any n choose 0, there's only one way to do that. And also there's n choose n, there's only one way to do that, right? And so 5 choose 5 has to be 1, and 5 choose 0 has to be 1. You can confirm it on your calculator, which is what I would do probably, right? But we know that this must be 1, and this must be 1. You can use the formula, but I'm just going to use the calculator. Yeah. I'll show you when I would want you to use this. There's a question on here. Where is it? Where is it? Where is it? Where is it? Where I get you to verify these equalities, right? Then I need you to expand the formula and use the formula, but otherwise you can use your calculator. That's fine. Okay. So 5 choose 4. How many ways can I choose 4 things? Well, there are 5 of those. 5 choose 3, we just found is 10, but you can confirm it on your calculator. You had to guess. 5 choose 2. It's also 10. Why? 3 heads is 2 tails, and 2 heads is 3 tails, but it really doesn't matter which one's which, right? And so that's why it's 10 and 10, and 5 choose 1. Oops. It's 5. Hey, it's a palindrome, sort of, and it is. 1, 5, 10, 10, 5, 1. Might look familiar. No. Maybe. Pascal's triangle. We're about to see it, so. It'll come up again. You add these all up, I get to 32. So there are 32 different ways that I could toss a coin and all the possible outcomes. How else could you have solved this? I think a little bit easier might have been or maybe secret. 1, 2, 3, 4, 5 tosses. I'm going to try to sneak it in here. I have 2 options, heads or tails, 2 options, 2 options, 2 options, 2 options. 2 to the power of 5 is also 32. So if you prefer, I'd say that's the easier way to do it.
What will I know? I should use that.
So in this case, when you're doing all the possible outcomes, I would maybe think twice about it. But we are going to see kind of questions where it's at least 1 head, right? And then it might not be so, or let's do 2 heads, right? I think we have one coming up anyways. But here, if you're looking at all the possible options, then I would just do the slots. But for 1 or 2 individually, I would use the choose function. But that is the pickle. I know that. Let's have a look at some more committees. So a committee usually starts as an unstructured set of people selected from a larger membership. So a committee is just a selection from this bigger group. So it's a combination. If a club of 25 members has a 5-member social committee, how many different possible social committees are there? So in this case, you want to think about, okay, does order matter? Right? So order matters in permutations, but it doesn't matter in combinations. So in this case, we're just going to say you're in the club or you're out of the club. Right? And so we can use the choose function. $25, choose 5, 5, 3, 1, 3, 0 ways of doing that. And I'm trying to think. Why 25 times 24 times 23 times 22 times 21 wouldn't work. They don't end up being the same number. And I know it's 25, choose 5. I feel like it should work. Unless I did it wrong. When I did 25 times 24 times 23 times 22, 1, 2, 3, 4. Oh, I get a different number. It's bigger. I don't want to say something false, so we'll just leave it at 25, choose 5 while I think on it a little bit. But I feel like it has something to do with either you're in or you're out. Right? And so the order inside doesn't matter. Right? So what I'm debating in my head is why can't, and here I'll do it in red, we can't do 25 times 24 times 23 times 22 times 21. And I'm leaning towards because the order doesn't matter, which is true. So in combinations, we'd have overlap here, I think.
divided by 5 multiplied by 4 multiplied by 3 multiplied by 2, 1, which is 120.
Well, 25 choose 5 is 25 factorial over 25 minus 5 factorial times 5 factorial, which is 25 time plus u times 24 times 23 times 22 times 21 times 20 factorial divided by 20 factorial and 5 factorial. It is the overlap. 20 factorial cancels with 20 factorial. And we're dividing by the 5 factorial. Yeah. Yeah, of course. You're allowed to leave without asking, of course.
Divided by whatever they're at. 4, and it'll be 5.
But I was trying to get to the bottom of why do you divide by 5 factorial? It is to eliminate the overlap, but on the spot, I'm not able to come up with it. But this is different than just this talk, right? And so that's what the choose function does. And that's when it would be different than just using the slots. Unless you divide it by 5 factorial. But like I said, I just can't get there right now. Sorry, guys. I'll think on it. That's okay. Maybe I'll call a friend. And by call a friend, I mean text a friend. Okay. More of these. You can see why I don't like having these. Unless they're ones that we have seen a pattern for many, many, many times, right? I'm not going to put them on the test. So, but we're just getting used to it. So if the club has a rule that the treasurer be on the social committee, then how many different possible social committees are there? So now the treasurer, I guess, has to be on the social committee, which means that one of those 5 spots is accounted for, putting us at 24 choose 4 times 1, which is the treasurer. And then this is everyone except the treasurer. (24) choose 4. 10626. Did they talk about the chairperson and the treasurer? I feel like we're missing some information. We're just supposed to know that there are treasurers and chairpersons. Maybe that's why it's not sinking in here, but it's okay. I'll tell you. If a chairperson other than the treasurer, so the treasurer is a chairperson, must be selected for the social committee, how many different possible social committees are there? And so here, assume there are a total of 5 chairpersons. And the treasurer is a chairperson. Kind of missing bits of information here. So then when we're choosing for the social committee, we're going to have the same situation, right? 24 choose 4 because one of the people from this secret chairperson group, I don't know where they got that from, sorry. I think I copy pasted too hard. 24 choose 4 times 4 from the total of 5 chairpersons, but other than the treasurer. And so I have 25 choose 4. So here is the chairperson. There are 4 options, right? Notice that essentially what I'm doing is I've got slots, sort of, but I've got the choose function in one of the slots, 24 choose 4, and then only 4 options for the next little guy. You don't have to think of it that way if you don't want to. 24 choose 4 times 4 is 42,504. I'd say the best little tidbit of this section, and including the choose function, bless you, is the binomial theorem. Now, the binomial theorem, it gives us a formula for expanding anything of the form x plus y to the power of n. And so you might remember if you have x plus y to the power of 2, for example, that's x plus y times x plus y. You have to feed the chickens, right? To the power of 3. Now you have x plus y times x plus y times x plus y. And so it just gives us a quicker way than feeding the chickens to expand these powers. Where n is a non-negative integer. And so the coefficients of this expansion are the binomial coefficients. And so what can we do here? If we have n, here I'll zoom in, whoop, just a general n, and I'll draw a line here. If n is 0, then anything to the power of 0 is 1. So far, so good. If n is 1, then I get x plus y to the power of 1. Fair enough? If x is 2 and I expand properly, I get x squared plus 2xy plus y squared. What I want you to start paying attention to is these coefficients are going to be the binomial coefficients. Okay. And so 1x to the power of 3 plus 3x squared y plus 3xy squared plus y to the 1 times y to the power of 3. All right, so here I've got 1, 1, 1, 1. Just adding on these coefficients that we don't usually have on here, right? But just so that we can see it, 1, 1, 1, 1. Does this look familiar? 1, 5, 10, 10, 5, 1. We just saw that. Right? So what could it be? 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5, maybe? Or because it's the same in reverse, right? Could be 5 choose 5, 5 choose 4, 3 2 1. There's also patterns here, right? If we look at x to the power of 5, so we started at x to the power of 5, then the next term, if we only focus on the x to the power of 4 and the y, right, we still have I think of it as a total of 5, right, in the powers. 4 plus 1 makes 5 still, right? It's just spread out. And so that's what's going to happen is we have x to the 3, y to the 2, right? And so the power on x seems to be decreasing 1 and essentially giving it to the y, right? And so, but the total power in kind of how I think about it is always going to be 5 if n is 5. Notice that also y to the power of 0, but anything to the power of 0 is 1, right? And here we have x to the power of 0, which we don't write. It's kind of hidden things, right? And so we've got this pattern, which we can leverage. So x plus y to the power of 5 looks like this. This is how it expands. Now imagine doing that. You could do that by hand. It would just be, you'd have to be nice and methodical. And that's just x plus y to the power of 5, right? X plus y times x plus y times x plus y times x plus y. As long as you do it nice and slowly, you should be done in about 2 pages, probably. Once you simplified and collected like terms and did all that fun stuff. It's not hard. It's just tedious. Or you can leverage the binomial theorem. And what we can do is we can rewrite that expansion, like we said, as 5 choose 0, right? X to the power of 5. 5 choose 1, x to the power of 4, y to the power of 1, right? And so here, 5 is telling me what my total power is, and then x to the 3, y to the 2, decrease x, increase y as I move through, right? Starting at 5 choose 0 and ending at 5 choose 5. And so we had that rule, right, that said that n choose 0 is 1 and n choose n is 1. And that's what we see here, right, as we move through 1, 1, 1, 1, 1, 1, 1, 1, 1. Another fun fact is that you can notice that 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. And 3 plus 1 is 4. That's cool. 1 plus 4 is 5. Why stop there? 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Then 1's on the end. So the expansion of x plus y to the n is going to look like this. So the first term is x to the power of n. So we start with x at the highest power. And the last term is everything's shifted over to the y's, y to the power of n. And with each successive term, exponents of x decrease by 1 and kind of give it to the exponents of y. And for any term, the sum of the exponents is n. Saw that, right? We saw they all added to 5. The coefficient of x to the power of n minus k y to the k is n choose k. Just work methodically, you'll see it. And the triangular array of binomial coefficients is called Pascal's triangle, which is after the 17th century French mathematician Blaise Pascal. And so this triangle keeps going and going and going and going, and Pascal's triangle just keeps going and going and going and going. When I was in computer science, we had to write a program to program Pascal's triangle, and man, was that hard for me because I don't think like that. Okay, kind of I guess it's embarrassing only because it's you guys. Any other class, they'd be like, "You're fine, Emily." But my dad's a software engineer, and so I got him to help me, of course. And he's Swedish, so he's like very deadpan too, kind of like no emotion. And so at one point, he looks at me and says, "Emily, I don't think programming is for you." I'm not claiming that it is. I just need to pass this course. I'm here to do math, but we had to take computer science, of course, at the time. So it is not, I get it now, sort of, but it's not my strong suit. So, but the binomial theorem I can get behind. Okay, so the binomial theorem, I just put it on here as a summary. So if n is greater than or equal to 0, and x and y are numbers, of course, so you can replace x and y with any numbers that you'd like, okay? Then x plus y to the power of n, now let's talk about the sum, is the sum from k equals 0 to n of n choose k, right? And so that's how we get that n choose 0, then n choose 1, then n choose 2, all the way up, times x to the n minus k times y to the k, right? As you move through each of those k's. Okay. We can use it to do things like find the third term in the expansion of x minus y to the power of 4. Now, notice that this is for x plus y. So whatever you do, you have to rewrite it as x plus y. And so one of the ways that you could do this, rewrite x minus y, oops, is you could say, well, that's the same as x plus negative y. That's how subtraction works anyways, right? And so I can rewrite this as x plus negative y, but now wherever I see a y in that formula, I have to use negative y instead. We're just getting started, right? The third term, we could jump right to it. What's k for the third term? Starts at 0, right? K starts at 0. So the third term would be 0, 1, 2, right? You could do that. Or you could do the entire expansion. That's probably what I would do. What do you want to do? We do the entire expansion just for practice. So remembering to use x where you see an x and negative y where you see a y. And I'm going to put this little guy here so we can see him. And then I'm going to start at the top. 420 times x to the 4 minus 0, y to the 0. A lot of these you don't need to write, right? 4 minus 0 is just 4, y to the 0 is just 1. And so you could just skip those if you wanted to. But I want to write them just so when you're looking back, you can see maybe where I got things from. Then I can move on to k equals 1. X to the 4 minus 1, y to the 1. K equals 2 now. Or choose 2, x to the 4 minus 2. Oh, what did I forget? I'm using y instead of negative y. Dun, dun, dun. Can I get away with it? I caught it before I finished, so I don't have to do it in red, right? I think. Or choose 3x to the 4 minus 3 times negative y to the 3 plus 4, choose 4. X to the 4 minus 4, y, negative y, okay, nice try, to the 4. We've got 4. So our coefficients are going to be 1, 4, 6, 4, 1. Or you can use your calculator. That's totally fine. But I'm trying to save us a little bit of time here. X to the 4 plus 4 times x to the 3 negative y to the 1. Negative y to the 1 is just negative y. So maybe I'll just keep it as negative y. You could even float that negative out front and make it subtraction, but I'll just keep it nice and clean for a little bit. 4 choose 2, I think we said was 6. X to the 2, negative y squared. A negative squared is just going to make it positive, so I can write it as y squared. Right? Or you can keep it as negative y squared if you want. But four choose 3 is 4, x to the 1, which we don't write, negative y to the 3. Negatives to odd powers stay negative. Right? But to even powers, they get positive. So the third term is going to be this one here. No. No, if you wanted to, you could have gone straight from here, right, and said, okay, then that looks like 4 choose 2. As long as you've identified that k must be 2, right, then x to the 4 minus 2 y to the 2. Oh, sorry, negative y. 4 choose 2 is 6 x squared y squared. So, or you could do that because it is just asking for the third term. But if you're not comfortable, then you can absolutely just list them all. But it might be a little tedious. Now I want you to do them all. It's only to the power of 3 though. So you could do it by expanding properly. But what are you going to do here? If you want to expand 3x minus 2 to the power of 3, then I would let 3x be x and plus negative 2 right? Because you need to get it in the form of x plus y, right? And so here, what you can do is you can let this be x plus -2. So if the y is replaced with -2. N is 3, so I have a power of 3. So let's do this thing. Okay. I have to expand from k equals 0 to n. N is 3. Right? So what I'm looking for here is I want the sum from k equals 0 to 3 of 3 choose k, x to the 3 minus k, but the x is going to be replaced by 3x. And the y is going to be replaced by -y to the k. Now I can cycle through k equals 0, k equals 1, k equals 2, k equals 3, and simplify as best as I can, right? But nothing crazy. So this is going to look like 3 choose 0, 3x to the power of 3. And because the negative y is to the power of 0, I'm not going to write it. We've outgrown that. 3 choose 1, 3x to the power of 2, -y to the power of 1, plus 3 choose 2 of 3x to the power of 3, -1 to the, nope, went the wrong way. 1 -y to the power of 2. Plus 3 choose 3, 3x to the power of 0, which I guess by the same logic I won't write, -y to the power of 3. Oh, thank you. Is it too late? Fine. Screwed up. 2. -2. At least I didn't drop the negative. Can do some simplification here. Right. I think it's 1331 for the coefficients. 1331. So then I get 3x to the power of 3 plus 3. Nah. You can just leave it like that. Why did I stop? You need 3 choose 1, but then you'd have to go 3 squared, x squared, -2, bring the negative up front. If we were supposed to collapse this whole thing, but the expansion is done already. So I'm happy there. Okay. I will add a hint here. For the very last question, you have to use the binomial theorem to calculate 9,998 to the power of 3. you can rewrite 9,998 is the same thing as 10,000 minus 2, or something like that. And now you've got an x plus y type of scenario. Or something else, right? Some other combo of x plus y is what you're going for. Oh my gosh. I can't believe you did it. Math boot camp. But now it's over. I'll stick around if you have any questions, but I'll also post the solutions here. So we're out of time, so I can't let you work on it. Well, I can. But nice work. You did it.